Hi everyone, my name is Shubham Pal. I'm a PhD candidate at the University of Michigan, advised by Professor Ron Dreslinski. And today I'm going to be talking about my thesis topic, which is towards closing the programmability efficiency gap using software-defined hardware. Traditional computing platforms such as CPUs, GPUs, FPGAs, and ASICs have been historically bounded by three conflicting constraints. They are algorithmic flexibility, hardware reconfigurability, and software programmability. Flexibility deals with the ability of a piece of hardware to execute diverse applications as well as to run updated versions of existing algorithms. For example, in the world of neural networks, where the algorithmic developments far outpace fabrication of new hardware. Next, we want the hardware to be fully reconfigurable in order to tailor itself to the characteristics of each kernel or application so that it is able to deliver near ASIC performance and efficiency. Given all this complexity, we further want the hardware to be programmable to actually facilitate adoption for existing users of general purpose processors under a small learning curve. During the initial phases of my research, I looked at accelerating irregular algorithms, particularly sparse matrix and matrix vector multiplication. We proposed a novel accelerator called Outer Space that uses single program multiple data paradigm with a reconfigurable cache crossbar hierarchy and HBM interface. We co-designed this with an unconventional outer product-based approach that splits the computation into a multiply and merge phases. The hardware is able to reconfigure between the two phases and thus efficiently execute SPMM and SPMV. We further prototyped a heterogeneous version of this architecture in 40 nanometer CMOS. In terms of results, we see about 10x performance improvement and 150x energy efficiency gain over state-of-the-art GPU. A die shot of the prototype is shown on the right, along with results which I'll be happy to discuss in the breakout session. I next looked at various other reconfigurations that could make the architecture amenable to a wider set of workloads. We thus proposed Transformer that uses fast reconfigurability to exploit efficiency across multiple algorithms. Transformer enables three dimensions of reconfiguration: memory type, sharing mode, and data flow within a short latency. And here I show 4 different transformer configurations out of 64 possible ones. Transformer further retains GPP level programmability using off-the-shelf cores and a full software stack called TransPy. TransPy allows the user to execute standard NumPy code on Transformer with just a single line of change of code. Our evaluation across a set of widely used kernel shows efficiency benefits of 18x over CPU and 4x over a GPU. We also achieve 4 to 2x over FPGAs and CGRAs and remain within 3 to 32x of ASICs, all the while remaining as programmable as a GPU. Our ongoing work focuses on two areas, which are intelligent reconfiguration and automatic code generation using a custom compiler. Thank you, and please join me in the breakout room for a deeper dive.